Hi Year 12 and welcome to this video on organic chemistry. Here we're going to look at alkenes and alkynes, the last two members of the hydrocarbon family. These hydrocarbons are unsaturated, meaning we're dealing with double bonds and triple bonds, spaces where more hydrogens could be added to the molecule, therefore we say they are unsaturated. First of all, alkenes. Alkenes have the general formula CnH2n, which means there'll be twice as many hydrogens as there are carbons in the molecule. The functional group is a carbon double bonded to a carbon, and the naming for alkenes will have a suffix, or the end of the name, ending in -ene. The position of the double bond and side chains must be indicated, and we use numbers to do so. And we always start numbering at the end closest to the double bond. Here are some examples that we'll go about naming. Here we have a 1, 2, 3, 4 carbon chain, whether you look at it going across this way or coming down. It's 1, 2, 3, 4. So this is going to be a bute. Because we're dealing with an alkene, the end of the name will end in -ene. I've left a gap here because we need to include a number to indicate the position of our double bond. In this case, the double bond is between carbons number 1 and 2, so we'll use the lowest of those two numbers, saying it's carbon number 1. So this is a bute 1-ene. We also have a 1 carbon side chain, and it's on carbon number 1, 2, 3. So we have a methyl on carbon number 3. So this molecule is 3-methyl bute 1-ene. Next example, we've got a 1, 2, 3 carbon chain, so this is a prop. We've got a double bond, so it's a prop-ene, and I don't need to include a number on this one because there's only one place the double bond can go, on an end carbon. If I move the double bond to this side, it would still be on an end carbon, and we would just start numbering at the other end. So whichever way you look at it, it's a prop 1-ene because there's only one place the double bond can go. We can leave out the 1 to say it's just a propene. Alkenes can form what's called stereoisomers. Stereoisomers have the same type and number of atoms and also the same connectivity. They're all connected in the same way, but they differ in their spatial arrangement, meaning they occupy three-dimensional space differently. There are two different types of stereoisomers, geometric isomers and optical isomers. Only the geometric isomers apply in alkenes. We'll save optical isomers for another video. Geometric isomers occur because the double bond cannot freely rotate. So we're going to look at an example here of bute 2-ene. Now, before we look at bute 2-ene, let's take a look at butane. I've got this model here, and I've got these green balls to represent a CH3 group or a methyl group. The black balls represent a carbon, and the white balls represent a hydrogen. So here is my carbon chain, 1, 2, 3, 4. That's a butane. They're all carbon-to-carbon single bonds. And one key principle here is that the single bonds can freely rotate. So it doesn't matter whereabouts these CH3 groups are because each orientation is effectively the same. It can spin around. Now to look at bute 2-ene. This is one possible version of bute 2-ene. Because we've got a double bond here, it cannot freely rotate. It's locked in this configuration. So it makes a difference if our CH3 groups are on the same side of the double bond or if they're on different sides of the double bond. Because they are locked in these configurations, they are locked in different shapes, and that can affect their physical and chemical properties. We need some way to name these two different geometric isomers of bute 2-ene. And so we call this version, where both the CH3s are on the same side or the top side of our double bond, we call that cis bute 2-ene. If they are on opposite sides of the double bond, we call it trans-butene. One helpful way that I like to remember this is that this forms a C for cis, and these ones are opposites. So if I'm going transatlantic, I'm going across the Atlantic Ocean. So trans-butene means our side groups are on opposite sides of the double bond. We're going across the double bond. The requirements for having geometric isomerism: the molecule must have a double bond because that cannot freely rotate. If it has all single bonds, there can be no geometric isomerism, no cis-trans. We must also have two different atoms or groups attached to each carbon of the double bond. So the reason for that is illustrated here by our molecule propene, which only has one side with two different groups, the other side has the same. Because these two are the same, it doesn't matter which hydrogen is on the same side as the CH3 and which is across on the other side. Because they're both the same thing, I can effectively just take the molecule and flip it over. There can be no cis-trans versions, no geometric isomers. Let's take a look at the chemical properties of alkenes. Addition reactions, where the double bond breaks and two atoms or groups are added to the carbon chain in its place. One example of this is halogenation. Halogenation is adding a halogen from either Br2 or Cl2, they're the examples that we see, and the halogens, remember, are group 17 on the periodic table, that right-hand side just next to the inert gases. So adding halogens to an alkene is called halogenation. The example we've got here is ethene reacting with bromine, Br2. And what happens is each bromine is going to add on to one carbon of the double bond, forming a haloalkane. So we've still got our carbons, all of this part is still the same, but you can see that I've broken this double bond, that's broken, leaving us with a single bond, and in its place I've added on my two bromines, forming 1,2-dibromoethane. Here we're going to look at the addition reaction of alkenes with Br2. So if I take some alkene, some hexene, and place a small layer of that on top of some bromine water, you can see again that it forms that separate layer. And if I give it a quick shake up, it reacts with it instantaneously, taking the bromine into the organic layer and reacting immediately. No catalyst required. This can be used to distinguish between an alkene and an alkane, where the alkane takes time and needs UV light to react. So just a brief reminder that as I add some alkane in here, it again is going to form that separate layer on the top, just like the alkene does. But this time, as I mix it up, it's going to pull the bromine into the organic layer, but there will be no immediate reaction, unlike the alkene. This is one way that we can distinguish between alkanes and alkenes by using bromine water, because the alkanes will react slow and need UV light, whereas the alkenes will react immediately and give this finished product. Another example we'll look at here is hydration, which is adding water. The example again, we'll use ethene, and we're going to add water, which I like to draw out as H to OH. I'm emphasizing the bond between the H and the O. And what happens here is, again, we're going to break our double bond, leaving it with a single bond, and the H will go on to one carbon and the OH to another. For this reaction, an H+ catalyst is required. So sometimes the reagent might be called dilute sulfuric acid, or concentrated sulfuric acid with water, or just acidified water. So when our H adds onto one carbon and our OH to another, we are again left with that carbon-to-carbon single bond. The hydrogens on the carbons are not changing, the ones that were originally there, they all stay the same. But we're going to put our H from the water on the left and our OH from the water on the right. In this case it doesn't matter where the H or the OH go, but in later examples they do matter. Another reaction that alkenes can undergo is hydrogenation, which is adding hydrogen, H2. For this reaction, a platinum catalyst is required. We're going to see the same thing happening here again, where our double bond will break, a hydrogen will go onto one carbon, a hydrogen will go onto the other carbon, and what we're going to form here is an alkane. So again, we've got our 2-carbon chain, our 4 original hydrogens are not moving, but we are now adding 2 hydrogens on. We've broken the double bond and left it with a single bond. That's hydrogenation. We can also react alkenes with hydrogen halides, such as HCl, there's the hydrogen, there's the halogen, hydrogen halide, or HBr, which is another hydrogen halide. They again will add to the molecule, causing that double bond to break. So again, we're going to have our 2-carbon chain with our 4 H's untouched, leaving a single bond instead of the double bond. And this time, we're going to add on H to this carbon and Cl to this carbon. H goes there, Cl goes there. So every addition reaction we are just breaking the double bond, leaving a single bond, and we add an atom or a group of atoms onto each carbon of the double bond. What should I do with the addition of unsymmetrical alkenes? So what happens if I have more than 2 carbons in my alkene, such as propene, and it's not symmetrical? There's no line of symmetry down our middle carbon. There are 2 possible things that could happen. My hydrogen could go to the middle carbon, or it could go to the end carbon. So I could have a hydrogen there, or I could have a hydrogen there. Likewise, my chlorine has 2 places it could go. It could go on the end carbon, or it could go on the middle carbon. So I could have a chlorine there, or a chlorine there. They form 2 different molecules. This is 1 chloropropane, this is 2 chloropropane. They will have different properties, so I need to be able to predict which molecule is going to be formed. To do this, we're going to apply a rule. The rule is Markovnikovs Rule. The carbon in the double bond that has the most hydrogen atoms attached will gain another hydrogen. Another way of thinking of this is that the rich get richer. The carbon that started off rich, which had the most hydrogens, is going to get richer and gain another hydrogen. So this is what will form the major product. The major product will be when this rule has applied, and that's the one we're going to get the majority of. The other option will be the minor product, and that's where the rich didn't get richer, the rich stayed the same. So we're always going to get 2 products formed when we're dealing with unsymmetrical alkenes, and the major product will be when Markovnikovs rule has applied, the minor product will be when it has not. So going back to our previous example that we looked at, the addition to propene, can we now identify which is the major and which is the minor product? Well, if we look at the 2 carbons of the double bond, the carbon on the right starts with 2 hydrogens, the carbon on the left only starts with 1. So this is our rich carbon, and this is our poor carbon. So the major product, the one we're going to form the majority of, is going to be when our rich carbon, the one with 2, gets richer. So it's going to gain the hydrogen. That is this option here, because our carbon on the right has gone from having 2 to having 3 hydrogens. The rich got richer. That is going to be our major product, meaning the other one is our minor product. So if I carried out this reaction, I would get a majority of this compound and a minority of this compound. It might be as much as 99% this one and 1% this one, or it could be 60-40 or any sort of other variation. But this will be the majority compound. Another type of reaction that alkenes can undergo is oxidation reactions. This typically occurs with permanganate, and where the permanganate undergoes reduction to oxidize the alkene. Where we have oxidation, we must have reduction, therefore our permanganate will undergo reduction, our alkene can then undergo oxidation. So let's have a look at this example here. We have an alkene, we're going to react with permanganate, and what this forms is called a diol. that's when we get two OHs, one on each carbon of the double bond. So there is our double bond. That double bond again is going to break. We're going to add OH onto each carbon, leaving us with this compound here. The permanganate can either turn into Mn2+, which would be a purple to colourless change, or it can turn into MnO2, which is brown. The product that it will turn into depends on whether or not this reaction is acidified. If it's acidified and we have H+, then our purple permanganate will turn into our colourless Mn2+. If it's not acidified and there's no H+, then our purple permanganate will turn into the brown MnO2. With the oxidation of alkenes, again, we've got our permanganate solution. On the left-hand side, I've got no acid in my permanganate. On the right-hand side, it is acidified. I'll add a small sample of alkene to each. And give them both a good shake up to observe the reaction. For the non-acidified, you can see a brown MnO2 product is formed. And for the acidified permanganate, it goes nicely colourless. So both of those were the oxidation of the alkene forming the alcohol, but if the permanganate is not acidified, it forms MnO2, which is brown. If the permanganate is acidified, it forms Mn2+, which is colourless. The last type of reaction that we need to know about for alkenes are called polymerisation reactions. A polymer is a long chain molecule made up of small repeating units. So here's an example of a polymerisation reaction, where we start with ethene, and these are the small monomers, and we're going to add them together where the double bonds will break, and effectively it's just going to form a big long chain where the double bond breaks and a single bond forms. Double bond breaks, single bond forms, and turns into one massive long chain with an undefined length. These are the monomers, and this is the polymer. So if our monomers were ethene, our polymer would be polyethene, which we commonly know as polythene, used to make many different types of plastic for waterproofing or packaging, etc. Here are some more examples of polymerisation reactions. Here we've got propene, which I've drawn in two different ways. This way emphasises the double bond, this way just is a regular sort of structural formula. And these propene molecules are going to combine to form our polymer, polypropene. Now, it can be more straightforward to identify what the polymer looks like if we draw our monomers like this, emphasising the double bond and then just hanging four different things off there, because effectively we've got that unit repeating many times. That's how we can identify what the polymer looks like. We can also draw that repeating unit like this, where we say it's this part of the molecule that's then going to repeat all the way down the molecule in number of times, or an undefined number of times. So to say it's a repeating unit, we say this one section is going to repeat, put some square brackets around it, and give it a little n on the outside to indicate that's the repeating unit. This would be polypropylene, which again is a common plastic, but can also be used in clothing, such as polyprops. Our third example here, we've got an alkene with a chlorine hanging off it. See if you can pause the video here and identify what the polymer might look like. And hopefully you've identified that that's what the polymer looks like. And if we were to identify the repeating unit, we would say that it's this section here, repeating n number of times. Or you could have done it on that one there as well. Both work. So that's all for alkenes. We're now going to look at our last member of the hydrocarbon family, alkynes, and the nice thing is, it's very brief. So, alkynes. Alkynes have the general formula CnH2n-2, meaning we take the number of carbons and double it to find the number of hydrogens, and then subtract 2. So if there was 4 carbons, there would be 2 times 4 is 8 hydrogens, but then take away 2 leaves 6. The functional group is a carbon triple bonded to another carbon. And as far as the naming goes, we have the suffix "-ine", so the ending of the name should end in "-ine". So ethyne, propyne, etc. Again, the position of the triple bond and side chains must be indicated. So here are two alkynes. This one has 1, 2, 3 carbons in the chain, so it's prop. The triple bond is at this end, so we'll start counting there. 1, 2, 3. It's got an alkyne, so it's going to end in -ine, and the triple bond is on carbon number 1. Now again, just like before, we don't need that 1, because if the triple bond was on this side, we would start numbering here. So wherever it is, it's always going to be on carbon number 1, so we don't really need that part in there. We could just call it propyne. Our second example here, we've got 1, 2, 3, 4, so it's bute. It's going to end in -ine because it's an alkyne with our triple bond. Now this time we do need a number because it could be in this position on the end, which would be bute 1-ine, or it could be in the middle, which would be bute 2-ine. Again, if it was on this end, that would also be bute 1-ine because we just start counting at the end closest to the triple bond. That's all we need to know about alkynes. We don't need to know any reactions. They behave similarly to alkenes, but we'll cover that another time. I hope you found this video helpful. All the best.